Hi, my name is Jiyan and I'll be talking about Phase 1. In Phase 1, we used the upper reinforcing concrete bridge connecting to building K and A, which we had to do for the drawing of a orthographic plan with at least 3 projections, which were top, side and front view, using AutoCAD, which shows the different materials that there is on each view. For example, on the top view, there is brick piers, angle where the brick falls, horizontal beam and vertical beams. Along with the orthographic drawings of bricks on AutoCAD, we had to create the bill of materials for each material, which is columns, vertical beams, horizontal beams, concrete slab, railing, brick piers and the brick flooring, which we had to measure the length, the width and the height, which we had to measure 3 times for each of the different materials to get the accurate measurement. To find the area, we had to times the length by width. For example, with the width, it was 0.3 and the length was 0.3, which gave us a total of 0.116 meters squared, which we had to do it for all materials to find the area. With the volume, we had to do the length times width times height for all materials. For example, we had to find out the mass, and how you do that is density times volume for each material. After we had done that, we have to work out the total mass, which comes from the total mass to find out the answer that you have to do is to get the total amount from the mass, then times it by how many materials you have gotten to find out the total mass. And you have to use these steps for each of these materials, which we gave a total mass of the bridge was 149/06.5 kilograms. The steps of the following with the bill of materials, we had to work out the uncertainty, which is getting the materials which are from columns, horizontal beams, concrete slab, railing, brick piers. From the materials, we had taken the 3 measurements from each material to work out the uncertainty, which is, for example, with columns, we have the 3 measurements. We have the high value of it and the low value. We divide that by 2. We get the total. Then we plus all 3 measurements. For example, for columns, it was 0.35 plus 0.32 plus 0.34. Divide by 3, you get 0.34. With the first answer, the high value was 0.35, take away the low value, which is 0.32, divided by 2, we had 0.34. We do plus minus 0.0153, and that is your length. And you repeat the same step with the width and the height to get the uncertainty. With all these steps you follow, you will go to Phase 2 and complete Phase 2.
Hi, my name is Monique, and today I'll be talking about Phase 2. In Phase 2, we used our previous data to then find dead loads, live loads, UDL, and also reactions. We started off by calculating all dead loads. The dead loads include structural members of the bridge itself. This included brick pier, columns, structural vertical beams, concrete slab, steel rails, the baluster, and we also assumed that the flooring was made up of bricks. To calculate the dead load, we used the mass from our previous data. Then we multiplied it by gravity, which is 9.8, and then it gave us each individual member's dead load. We then calculated the total dead load, which we added all of them up together, and it gave us 271,046 newtons. We then moved on to finding our live loads. For example, the bridge's live load would be people walking on the bridge. Therefore, we needed to consider the bridge's use to help us calculate this. To find the live load, we needed to find the KPA, which is known as the pressure. We used Australian Standard 1170, Table 3.1, and found that the KPA that was most suited to the bridge. we assumed that we would use 4.0 kPa. To get the area, we multiplied length by width, and then we multiplied the 4.0 kPa by the area of the slab. For our final result, we got 550,720 newtons. Next, we found our UDL, which is known as uniformly distributed load. This is where the load is distributed along the beam. To find the UDL, we assume to use the concrete slab volume that is distributed along the two beams. We used the formula density times volume times gravity and then divided it by the length. So in our case, our density was 2,400 times our volume, which was 48.11, and then times the gravity, which once again is 9.8. Then we divided that by the length, which was 17.88, and it gave us 63,285.64. Then we multiplied the pressure, which was 4.0 times width. We converted the kPa to PA, so then the 4.0 goes to 4,000 PA. Then we times it by the width, which was 7.7, and it gave us the value of 30,800. To get the total UDL, we added those two results together, which gave us 94,085.64 newtons per meter. Because we are only using one beam, we needed to then divide it by the two beams to get our final answer, which resulted in 47,042.82 newtons per meter. There were some errors when we first calculated our UDL. Once we were aware of this, we went back and checked all calculations, and the reason that we needed to fix this is because we needed it for our next phase. Next, we looked at reactions of the bridge. We needed to consider that there were three supports, the three columns that were holding the beam and the concrete slab. Our first attempt at reactions, there were also some errors, so we needed to go back and fix this. We then related Newton's third law to the bridge to then help us work out new reactions and found a way to see if our reactions were right. Newton's third law suggests that for every action there is an equal reaction, therefore meaning in this case that the action on the bridge, which was our UDL, has an equal reaction. This means our reactions should be equal to our UDL, newtons per meter. We calculated that the whole beam was 846,770.4 newtons. We then separated the diagram as we assumed that this would be the way to calculate all three support reactions. We then calculated reactions from support RA to support RB. We multiplied the UDL by the length between RA and RB. We then divided this by 2 as there are two supports, which then gave us 198,050.2 newtons for RA, and at this point RB being the same. We then did the same from RB to RC. From these supports, we got 225,335 newtons. To find support B's reactions, we added both values together, which gave us 423,385.2 newtons. Being as RB is the center support of the bridge, it would support the bridge the most. To check our answer, we added all support reactions together, giving us an equal reaction to all forces going down.
In phase 3, we have learnt different types of loads and forces. Mainly, we have learnt about shear force and bending moment. If we talk about shear force, these forces are unaligned forces pushing one part of a body in one direction and another part of the body in opposite direction. In this slide, you can see the shear force diagram of the bridge. To find out forces and moments, we've used equilibrium equations. There are three equations. First two are used to find out forces and the third one is for the moment. We've used first two to find out the shear force and the third one for the bending moment. Bending moment is the measure of internal stress that produced by the external forces or moment causing the element to bend. In bending moment, there are two kinds of forces. One is tension, which pulls material apart, and the other one is compression, which squeezes materials together. In this whole unit, we have learnt things in 4 different phases, as you can see in the slides. Making groups was a great idea to teach us teamwork. because I think in this field, one person cannot do everything alone. We need to learn cooperation, patience, and how to work together to sort out things. I really enjoyed working with my team together. Thank you.